Alright, we'll go ahead and get started. We're going to start a new section today. This is going to be essentially the last derivative rule we're going to be using for the corner, unless I need to go back and do logs. Okay. So number 17 on the online homework. And again, the numbers might be different than yours, but it says find f prime of x for f of x equals 24 times the cube root of x over, and then mine has x squared minus 5 in the bottom. So is yours the same, roughly, kind of?
Yeah, it was either 5 or 3, one was 9.
Okay, so yeah, I think it'll be the same idea.
Plus x to the 4 times that.
So we all ready to roll? Okay. So, you might have remembered me saying this earlier, but in calculus, radicals are almost never helpful. Okay, so what you should do is always convert a radical to fractional exponent form first. So this would be 24, and the cube root of x is the same as x to the 1/3. And then you'll have an x squared minus 5 on the bottom. And we'll go through the simplifying part too, since they want you to. Okay, so first write it in fractional exponent form. And then let me just pass these out while people are kind of copying that down.
Pass these behind you for me. These three.
And Amanda, could you do me a favor and slide these three behind you? And you already did go through the survey, and then if you want to share Scott and Len.
Get that 45? Get that 45?
Oh, Nathaniel, here's your test, by the way. Can you reach me? Okay, so this is now a quotient, right? So we do the quotient rule. And the quotient rule says you're going to obtain, again, the derivative will be a quotient. And what do you start with in the numerator?
The bottom.
Always start with the bottom function. So you'll have x squared minus 5 times. And then you'll take the derivative of the top function. And it's just going to be pull the 1/3 out front, multiply by 24, and then do x to the next lowest power. 1/3 of 24 is 8. Let me find a better marker here. There you go. 1/3 of 24 is 8, and then you do x to the next lowest power. So you have to do 1/3 minus 1. That's 1/3 minus 3/3, and you'll get minus 2/3 for a power. So I did bottom function times derivative of the top. We just pulled the 1/3 out front, and the next lowest power when you subtract by 1 is minus 2/3. And then you subtract the top function times the derivative of the bottom, but the derivative of x squared minus 5 is just 2x. And then you always divide by the bottom function squared. Okay. Now let me see. Again, sometimes I just have to see how far they want you to go to simplify something.
Yeah, the part that was messing me up was at one point they put the negative 2/3 down on the bottom, and then they multiplied by 2/3 on top and bottom to cancel out the negative 2/3 or the 2/3 from the bottom.
Yep. So what they're doing is they're looking at these two fractional exponent terms, and when you factor out a power of x, do you always factor out the higher power or the lower power? The lower, right? So think in a simple case, if you were factoring x squared plus x, you can factor out the x. So what they're doing here is really x to the minus 2/3 is the lower power. So they factor that out.
Well, they didn't necessarily factor it out. They multiplied by the 2/3, 2/3 to cancel it out.
Oh, that would work too, actually. So that's equivalent to what they're doing. So generally I do a factoring out instead of multiplying on top and bottom, but Yeah, you could also multiply the top by x to the 2/3 and the bottom by x to the 2/3, but I just always factor out the lowest power.
Okay.
And then what's left over is 8 times x squared minus 5, since you pulled this out of the first term, minus 24, well, let me do something here. 24 times 2x is really going to be 48x. And then you're going to have x to another power. Okay. So all I did here was I left the 24 times 2x inside the brackets. And then what the power is here is going to be, what do I have to add to this to get back 1/3? Because now if you redistributed this, it's going to be x to the minus 2/3 times x to this power. And when you multiply with the same base, you add exponents. Anybody have a guess? What power do I need here so that this power plus negative 2/3 gives me positive 1/3?
3/3.
It'll be 3/3, or we can just leave it as positive 1. Okay. And then what they do from here is they take something with a negative exponent and bring it to the bottom with a positive.
Yeah. This makes more sense than what they were doing.
Yeah.
Yeah. Again, sometimes the question help, you got to be wary. It just everybody has different ways of simplifying things, and some what works for somebody might kind of be convoluted to the next person. And then you just have to simplify what's in these inside this bracket here. So you'd have to distribute the 8. That'll be 48x squared. I think I can see it from here. Let's see. 8x squared minus 48x squared is a minus 56x squared. And then you're going to have an 8 times minus 5 and get a minus 40. So that's what they would want fully simplified. Unless I made a mistake somewhere.
No, that looks.
No, I did though. 8x squared minus 48 is really minus 40.
Yeah, that's what most of the answers looks like.
Yeah. Okay. So generally what you do is once I do the quotient rule and I get this expression in the numerator, I try to see if I have any powers of x or anything I can factor out. You could have actually combined these two powers of x first and got x to the 4/3, but you'd still factor out the x to the negative 2/3. Okay. And like I said, we'll be doing a lot more of that later. So unfortunately on the online homework they make you simplify. Although I don't really think it's all that unfortunate because it's really good algebra practice. And again, since we're going to have to do a lot of simplifying later and solving equations with derivatives, it's good practice to do it here. Okay, any other quick questions? I think since I spent yesterday going over the test, I'd probably like to move on and start section 3-4. Now, on the handout I passed out, really all I've done here is this. I've got a summary of all the rules in this section. So I'm just going to be making up problems, and then you can maybe write them in your notes. So on Monday, I'll come up with like a worksheet. We'll do some marginal analysis stuff again for practice. Is it okay if I erase what's up here? You good? Okay. All right, so what we're going to do first is we're going to talk about something called the general power rule. And then we're even going to talk about a more general derivative rule called the chain rule. So before I do anything, how many people have seen something like a composition? Actually, let me use the notation. Well, I guess the notation they have is kind of weird. But how many people have seen this fog or F circle G? Hopefully everybody. So this is notation for the function f composed with g. And the way it's defined is you first, whatever the input x is, you plug it into g of x to get an output for g. And then that output gets then plugged into f. Okay. Where you see compositions more often, you might see something like, say, e to the x squared. Okay. So say this is like your, I don't know, I'll make up a letter. Say that's h of x. This can be rewritten as a composition f circle g of x. Okay. Now, one of those functions is going to be called the inner function, and the one on the left is called the outer function. Now, generally, if you have an exponent to a power, the power is really the inner function, and the exponential is the outer function. So, if I define f of x to be e to the x, and g of x to be the power x squared, and then watch what happens when I do f circle g of x. So now, f circle g of x, that's f of g of x by definition. And then what you do is I replace g of x with its expression x squared. And then what does f do to an input? F takes your input and makes it the power on e. So this would become e to the x squared. Okay. So that's how I take my single function h of x and break it up into a composition. Okay. And that's our goal today, is learning how to take derivatives of these compositions. So we're going to start with a basic one first. So this is called the general power rule. Maybe it's a good idea if I do this too. How about I write down the original power rule? So remember, if you just had x to a power, if I want to take the derivative with respect to x, well, we just used this in the previous problem, but the power comes out front, and then you do x to the original power minus 1. Okay, so that's the old power rule. Now, instead of having x to a power, what if your f of x is really some function raised to a power? So it's not just x anymore. Okay? You might have some other function raised to a power. What the general power rule is going to tell us is you use the power rule on the outside. So the n can still come out front. And then you still reduce the power by 1. But then you have to remember to multiply by the derivative of that function being raised to a power. I'll probably do an example before we look at the general chain rule. Okay. So if you have a function raised to a power, rather than having to multiply it and FOIL it or expand it out, you can just take the derivative this way by bringing the power out front, reducing the power by 1, and then multiplying by the derivative of the function being raised to a power. So I think an example might make this make a little bit more sense. So what if I had, so I'll call this example 1. If f of x was x squared minus 4 raised to the 4th power. Now, before this section, what would I have to do to find the derivative? Well, you could write it as x squared minus 4 times x squared minus 4 times x squared minus 4 times. And then you could do repeated iterations of the product rule, which would suck. Or you could just multiply and expand that expression out, which would also suck because it's a 4th power. Okay? Excuse my language. It just wouldn't be very fun to have to multiply that thing out. So now what we can do instead, f prime of x, this rule says the outer power can come out front. What's inside the parentheses will stay the same. And then you reduce the power by 1. So this is 4 times x squared minus 4 to the next lowest power. But if I just stopped there, I would be wrong. Okay, you can't just do the power on the outside and bring it down and be done. It says you also have to multiply by the derivative of what's in the parentheses. And I'm going to be careful. I'm going to write the derivative notation. So I also have to multiply it by the derivative of the function inside the parentheses. So this will be 4x squared minus 4 cubed times, and then what's the derivative of x squared minus 4? That'll just be 2x. And then, of course, you can simplify a little bit. I can instead write this as 8x times x squared minus 4 to the 3rd power. So I just did the 2x times 4 and put it out front. Okay. Now go home and expand that x squared minus 4 to the 4th power out and see how long that takes. Won't be very much fun. It'll be good practice for your algebra and your foiling and your adding together like terms, but it's probably not worth our time. Okay.
So that's the final form.
That is the final form, yep, of the derivative of the original function. Okay, so again, essentially if you have some function to a power, you use the power rule on the outside and then just keep the inside the same, but make sure you multiply by the derivative of the inside. Okay, this would also work with things like this. Let me do one more. So let's say f of x was, I can actually do this time. Let's see, what if I want to do, so I wrote this on purpose like this. Okay, so 2 divided by, and then in parentheses 4 minus x to the minus 2 with a minus 2 power on the outside. Okay, and then here's another thing that I guess becomes a little bit more difficult, is you can always take your function as written and apply your derivative rules that way, or is there some way you can rewrite the function and maybe simplify it? So if I wanted to apply a derivative rule, this is ultimately a quotient. So I could use the quotient rule here. However, anybody know of a way I can maybe simplify the expression and avoid using the quotient rule? Yeah, so bring something up, right? Since we're dividing by something with a negative exponent, this could instead be written as 2 times 4 minus x to the minus 2 with a square power instead. So instead of dividing by something with a negative exponent, we can multiply by the same expression with a positive exponent. But you could have used quotient rule right away if you wanted to, and we have the tools to do it. But generally, I avoid the quotient rule if I don't have to use it. Okay. So now you're thinking constant multiple rule. I have 2 times the function. The derivative is going to be 2 times the derivative of this function. So we're just taking 2, and we're multiplying by the derivative of that function to the power. Okay, so now we need to multiply by the derivative of this. Okay, so what does the general power rule say I can do? This 2 can, not the Fruit Loops bird, but this 2 can come out front. Hey! Okay, so you bring the 2 down front, reduce the power by 1. Make sure you keep that function in the parentheses the same. Then I multiply by the derivative of what's inside. Okay. And then the derivative of 4 is 0. And then for the second term, the minus 2 can come out front to give us 2x to the next lowest power, negative 3. And then you could simplify this a little bit. 2 times 2 times 2 is 8. And then I can write it as 4 times x to the minus 2. And then instead of doing x to the minus 3, I can divide by x cubed. Okay, so the 2 times 2 times 2 gave me the 8. I kept the 4 minus x to the minus 2 in the numerator. And the x to the minus 3 I just brought down with a positive exponent. And there would be your derivative. And again, these are really composition of functions. Like this was the composition of x to the 4th with the function x squared minus 4. So the inner function is x squared minus 4. The outer function is just the x to the 4th. But now we're going to generalize this a little bit. So not only does this work for function raised to powers, those are special compositions. Okay, now you can do this in general for any composition. How do you have time? Make sure this is still working. Okay. So now the chain rule, theorem 2. Okay, so if your original function is m of x, I don't know why they chose m. I do have some idea of why they chose e and I. Anybody have a guess? I for interior function, E for exterior function. Okay. This book has some hang up or some, it likes to define functions that in a meaningful way that help you remember. Okay. Yeah.
How do you know when to stop simplifying? Like on example 2, couldn't you technically keep distributing the 8 and simplify it further?
Yeah, I guess.
Well, but you don't have to. I'm just saying, should we stop right there? Or?
Yeah, I would say, simplify as much as you can. You could try plugging it into like the online homework and see what they say. It depends on what you're going to do with this. The only thing I could really do from here is you should probably simplify in a way that doesn't leave you with any negative exponents. So really, and I'm going to do this because I think it's good for us all. The x to the minus 2 could be rewritten as 1 over x squared. And then you could clear this denominator by multiplying the top by x squared and the bottom by x squared. So this would be 8. And then if you distribute the x squared inside, you get a 4x squared, and then 1 over x squared times x squared is 1. And then you'd get an x to the 5th in the denominator. And then, yeah, you could distribute the 8 if you wanted to. Okay. So generally, simplifying means rewrite everything so there's no negative exponents, generally. So maybe that would be a better simplified form. Okay. On the test, I'll probably say something like, find the derivatives you do not need to simplify. Unless it's a problem like, where's the tangent line horizontal? Well, then you're going to have to do some algebra, because you'll have to set the derivative equal to 0 and solve. Okay. Usually I like to simplify it first so it doesn't have any negative exponents before I set it equal to 0 and solve, but you can do it either way.
Okay, thank you.
Yep. Okay. So, anyways, yeah, back to the general chain rules. So if that's if n is a composite function, so you're plugging some function into another, and then if these derivatives exist, the derivative, and it's really similar to the previous one if you think about it, you take the derivative of the outside function and keep the inside function the same, and we did exactly that here. Because the outside function is just a power function. So you took the derivative on the outside, and then you multiplied by the derivative of the inside function, which in this case would be I prime of x. So another way of saying this is, it's the derivative of the outer function evaluated at the inner function times the derivative of the inner function. And then I'm going to give you a bunch of general derivative rules now, like involving e to the x, or general exponentials. I don't know about a bunch of them. I think we only have a couple. So, do you remember in a previous section where I told you, especially this came up when we did the compound interest formula and needed to take the derivative if you had e to the c times x? Sorry, this is our general derivative rules. I told you the derivative of this was just c times e to the cx. So this is just coming from the chain rule. The exponent is the inside function. The derivative of the outer function is the same thing, and then times the derivative of the exponent would just be c. Okay, so that's really a result from the chain rule. Okay. And then I'll tell you in general, this doesn't work for just e to the cx, but what if I have e to the f of x? Okay. So the outer function is e to the x. The derivative of e to the x is e to the x evaluated at the inner function. So this would just be the same thing. That's the derivative of the outside evaluated at the inside times the derivative of the inside function, which is just the derivative of the power. Okay, so if you have e to any function of x, the derivative is just the same thing times the derivative of the exponent. So this is a generalization of this even. Okay, what other ones do we have? I think we also have general bases. So if it's not just b to the x anymore, this one I'm going to write down the original rule. I'm going to see if anybody can guess this too. So if I just had the derivative of just b to the x, we know that's natural log of the base times b to the x. Okay. So again, b to the x is the outside function. The inside function is the power. So anybody have a guess? The derivative of the outside evaluated at the inside is going to be taking this exact expression, and instead of having an x, it's going to be natural log of the base times b to what? So it'll be b to the f of x. So that's the derivative of the outside evaluated at the inside. And then I'd have to remember to multiply by what? The derivative of, what'd you say, Chloe?
F of x.
Yeah, so it's really going to be an f prime of x, yep. Okay. So this is the derivative of the outer function evaluated at the power times the derivative of the power. Okay. And these three rules together with the general power rule should basically let us now take derivatives of anything we need to. Other than log stuff, but... So those are generalizations now of derivatives using chain rule. Since we don't have to worry about trig functions in this class, or and maybe we don't have to worry about logs, there's really not, I don't think, that many functions we have to worry about. Let's see how we doing on time, like 20 minutes. Yeah, let me give you a couple examples to try. Am I on 3?
Yep.
Okay. So let's find, I'll say y prime if y equals 4e to the x cubed plus x. See what you come up with. Yeah, Nathaniel?
Are we going to be taking second derivatives in this class?
Yes.
So wouldn't it be beneficial to do log then? Because isn't the first derivative of an exponential include a log? So if you take the derivative of that, you need...
Yes, except for the log piece doesn't have any variables. It just has constants.
Okay.
So,
good to know.
yeah. So yeah, you still don't have to worry about derivatives of logs.
Awesome.
Although, since you want to take general calculus classes, it might be beneficial to look into those.
Yeah.
So basically, you're getting everything but logs and trig functions. All right, so hopefully everyone's thought about this for just a minute. Okay, a couple things we're using. This is a constant multiple of a function for starters. So your derivative is going to be 4 times. And then what's your general derivative rule say for e to a function of x? It says if your power is a general function of x, the derivative is the same thing times the derivative of the exponent. So what's my derivative going to be? So I'll write down the same thing and then multiply by the derivative of the x cubed plus x. Since your derivative has two terms, you're going to want to introduce parentheses. And what did we get for a derivative of the power? So 3x squared for the first term plus, and the derivative of x is just 1. And there's actually no simplifying to be done here. That's actually as simple as it can be written.
That's awesome.
Yes.
Because it looks like a nightmare if you did try to simplify that.
Yeah, I mean, I guess the only thing we could really do, and I don't know if it's, I guess it's already in a factored form. If you multiply everything back out, it's not really as, I guess it's not a factored form anymore. This is actually easier to work with. Say I wanted to find where the tangent line's horizontal, I'd set this equal to 0 and solve, although this will never equal 0. E to the x, or e to any exponent's always positive. If you look at the graph, it's always above the x-axis. Well, x squared is greater than or equal to 0, and you're adding something positive. So this derivative is positive everywhere, which means this function is always rising. If you look at its graph, the original function. Okay. Let's try something with a general base. Let me write this one back up here. So let me mix some stuff up. What if, how are we on time? Oh, we're doing pretty good. What if I say, let's find, this time I'll use the Leibniz notation, and I'm going to switch it to t's. What if I want d over dt of, let's say, 2 to the x squared over 1 plus x squared squared. So now I'm starting to bring in other rules on top of the rules we already know. So here you're going to have to use the quotient rule first, coupled with the chain rule while you're doing it. I want everyone to work on this for maybe like 4 or 5 minutes before we do it together. So start by applying quotient rule, and then you might have to use our new rules while you're doing that. I can come around if anybody wants me to check and see if they're on the right track. So here's where you have to be careful, because that's really an exponential with the power being x squared. So you'd be using that. But you have the right idea, starting with quotient rule.
So what would be 2x squared?
2 to the x squared power times natural log of the base times derivative of the exponent.
Square front. So
Base 2. Oh, you're needing the derivative of x squared exponent. 2x, right?
so but this is right too.
Yeah, although just make sure that the x squared should really be the power on 2. Was that clear to everybody? That this is supposed to be the power. That's the power on a base 2. So that's something of this form. Okay. So maybe it's okay to intervene here. So if you're going to start using the quotient rule, because ultimately this is a fraction or a quotient, what is it? The bottom times derivative of the top. And we're using this formula where the base is 2 and the f of x is x squared. So it says you do natural log of the base 2 times the same function and then times the derivative of the exponent. It's kind of weird when you have a power to a power. Okay, so again, this is a base to a function of x. And then it's going to be, so that's the bottom, that's the derivative of the top. And then what's the sign in the middle in the numerator? It's always a minus sign. And then you do the top function times the derivative of the bottom. Now we're using the general power rule. That's the first rule I put on top of your handout. So we want, I'll do it on the side. We want the derivative of 1 plus x squared with this outer squared power. That's what we're going to multiply by here. So what do?
The 2 comes out front.
2 comes out front. The inside stays the same. The power gets reduced to a 1, and then you have to remember to multiply by the derivative of the inside, which will just be 2x. So here you get times 4x, and then in parentheses a 1 plus x squared.
And you have to put the other term in parentheses too.
No.
Where the minus sign is? Like right after the minus sign?
Nope, I can leave it just like this.
It's 1.
Oh, I thought
You can do minus, there's no plus, there's no addition anywhere. These are all just multiplications, so I don't need parentheses.
Okay.
And then you always, once you do bottom times derivative of the top minus top times derivative of the bottom, you always divide by the bottom squared. Now I don't want to rewrite this whole thing again. I guess we could simplify. Actually, we'll simplify this for practice. But what happens when you square a square? The power is going to become a...
Oh wait, it's going to multiply, right?
Yep. Well, let's just do this. Since we're going to simplify anyways for practice, I'll do the bottom squared rather than skip any steps. Okay. And then now we're going to factor this thing as much as we can. Simplify. This is actually probably good that I did something like this so everybody can see how to do the simplifying when it's really messy. We'll probably call it a day after this too, if that's all right with everybody. On Monday, what we'll do is I'll probably just do one application, like a marginal analysis business economics application, and then we'll probably start something new on Monday as well. Now, the next 2 sections, make sure you might want to do some reading on the front end. The next 2 sections tend to be a little, I wouldn't say they're hard, they're just, it's strange, it's different. Okay, so maybe make sure you read ahead a little bit before you come to class. And then I'm really excited because section 3.6 or 7 is the elasticity of demand. And that's one of my favorite applications. So we'll be doing a whole section on just elasticity. Okay. So what you're going to do now is you're going to look in the numerator and you're going to try and see, right, you've really got 2 terms. They look really messy, but there's 2 terms up here. So there's this term and there's that term being subtracted. And let's think of all the common factors we could pull out. Well, certainly I see a 2 to the x squared in both terms. Okay, so that can be pulled out. Okay, any other common factors?
2x.
There's a 2x floating around. So I can factor a 2x out of a 2x and a 4x.
And then you can take out one of the 1 plus x squared.
Okay, notice you have a 1 plus x squared here. And you've got another one there. You can pull one of those out. Okay, now I think the factoring things out is the easy part. I think maybe the hard part is what's left over inside the brackets. Also, I can do this right away too. When you raise a power to a power u, you said you multiply, so this becomes a fourth power. Now, what stuff is left over? I already pulled the 2x out. I already pulled this. Ah, the ln is in there still. And how many of these did we pull out? We just pulled 1. So you still have a 1 plus x squared. So if I take all this junk and multiply it by this term, you'll get back the first term we originally had.
There's still isn't there still a 2x in there?
Is this one right here?
Well,
We got
no.
on the other side.
Oh yeah, I'm just pausing for a second. We still have minus what's left over in the second term. But you said that all that's left is going to be a...
It should just be 2 though, isn't it?
Yeah, it's just positive 2 because we already factored out a 2 to the x squared. And we already factored out the 1 plus x squared.
Oh, yeah.
And we factored a 2x out of 4x, so there's just a 2 left over.
And then we can cancel the 1 plus x squared on the top with one of the ones on the bottom.
Beautiful. And that would be as simple as we can write this thing. So when you're done, it's 2 to the x squared times 2x times, and this 1 plus x squared is going to cancel, and that's going to become a 3. And then you'll have natural log of 2 times 1 plus x squared minus 2, all over 1 plus x squared to the third power. Okay. So this is a little bit of a preview of what we'll be doing a lot more of later. Now, the only reason I'm really good at this is because I did lots of what? Practice. Okay, I guarantee you I'm not a very smart person. Okay? Or at least I don't think of myself as one. Okay, and what was interesting is when I took like pre-cal 1 or the equivalent, I went to the front of the book, and there was a bunch of problems where you already had expressions like this and you had to factor them. So I did a lot of practice on this in pre-cal 1, so when I got to calculus, I was already pretty primed for this. But what's unfortunate is our pre-cal 1 class and lots of other schools, they don't really have you do this much complicated factoring. Okay, so a lot of times students see this for the first time in a calculus class, which is okay. It just means you have to do lots more practice because you're not as familiar with it. I don't think a lot of them are going to be as nasty as this. There's certainly not going to be mixtures of these exponentials and polynomials and stuff. But anyways, we'll stop there for today. We'll do some business stuff on Monday and start a new section. Maybe, again, make sure to take a look at section 3.5 before you come to class. Oh, yes. Nobody leave yet. Do you have the take-home quiz today?
Oh, I was like,
That's fine.
I'll just kind of stand back here and pass them around on the way up. Make sure you look at both sides. There wasn't really a whole lot of information. Did I give you one, Sergey? You got homework for me, or you got a question?
Homework with questions.
Okay, I'll wait. And we need 2 here.
Yeah.
And did you get one?
What's up?
Yeah, I
Oh, yeah,
had
that
the
one.
question.
Let me take a look at that for you.
So it's just this one. I think it's okay, but so I even should have set it up the right way. So when I actually set it up to write equals a function,
I added that extra zero, that's why you corrected it there.
Hmm.
But I didn't mean to add that extra zero on there. I don't know why.
Yeah, so this is what you really should have had.
Yeah.
It's this, and then this isn't technically the derivative.
Yeah,
because you're missing it.
I-
Okay, I'll throw you a point.
Okay, thank you.
Yeah, no problem. Let me pause this, and I'll take care of that.